Hello, and thanks for checking out Chemistry Connections on the Hopewell Valley Student Podcasting Network, a proud partner of hvspn.com, where students come together to publish content to share with the world. The opinions represented within this episode are those of the content creators only. Please enjoy the show.
Hello, welcome to Chemistry Connections. My name is Ben Ault, and I'll be your host for episode number 4, called The Chemistry of Minerals. I'll be discussing the chemistry behind the formation and the properties of minerals. So first I want to start out with kind of an introduction on what minerals are and a general overview of the topic. So minerals are a classification of substances that are formed naturally via geological processes and form crystalline structures. More specifically, this means that they're formed by different elements undergoing reactions deep underneath the Earth's surface under extreme temperature and pressure conditions. Another part of the definition of a mineral is that they have to be relatively uniform in their chemical composition. Of course, they can have some minor flaws in their structure, but for the most part, this results in consistent properties between samples such as color, luster, or hardness. And for a substance to be a mineral, it has to be made of a crystalline structure, and it has to be completely homogeneous and can be assigned an empirical formula. The most easily confused distinction in this topic is between rocks and minerals. A lot of people use these terms interchangeably, but they're actually two different things with two different definitions. There are two types of rocks, and the ones that most people are probably familiar with are called polymineralic rocks, and some examples are like granite or marble. And these types of rocks are made of non-uniform mixtures of different minerals, and these rocks are not minerals themselves. So they might be made of a bunch of different species of minerals that each could form a rock, but when they're all mixed together, these rocks can be assigned new names and they're not considered minerals. The other kind of rocks are monomineralic rocks, and these are minerals. Any type of solid, homogeneous, crystalline structure that's found in nature is a mineral, and this includes quartz crystals, limestone, and ores like bauxite, and even ice, as long as it is frozen naturally, like found in glaciers. The difference in the properties of minerals is caused mainly by two factors, those being elemental composition and the bond structure. And this means that two minerals can be distinct despite having the same elemental composition. This is called a polymorph, and they can display extremely different properties. These factors also have to do with how minerals are classified, and there are a ton of different classifications based on these factors, and some of the groups include like metallic or non-metallic. They can be classified by crystal type or the hardness of the material. That's just to name a few. And a lot of generalizations can be made from these classifications, which helps to predict the mineral properties without testing the actual composition of them. And everything that I've mentioned so far is a result of the atomic behaviors of the elements that compose each mineral. So all of these phenomenon and patterns can be explained by delving into the chemistry within each mineral. As I mentioned earlier, many minerals are formed under extreme conditions, like those in volcanoes. And the reason for this is because these are the conditions in which the extreme temperature and pressure can melt the rock and allow it to undergo reactions. Reactions happen a lot easier if they're in an aqueous or liquid form. And that's kind of what happens in the lower crust of the Earth and the mantle, into kind of like a soup of elements. Some of the most common ions in these pockets are silicon, oxygen, aluminum, and iron. And if you just look up some of the common formulas of like rocks like granite or marble, you'll see that a majority of it is made up of silicon, oxygen, aluminum, or iron. While these ions are in the liquid state, they can kind of freely flow within the pools of magma, And as this liquid rises towards the surface, it begins to cool down as the pressure decreases. And once they begin to cool down, they exit the liquid state, and these ions begin to form the crystals as they solidify, and they precipitate on other rocks and surfaces to form minerals. This can take an extremely long time for some elements, and the reason for this is because the individual ions have to hit existing crystals in just the right way in order to properly arrange themselves to form this crystal structure. And if they don't, they'll just kind of bounce off. And on top of that, they need enough kinetic energy to overcome the activation energy of formation of these minerals. It's also possible for other elements to bond to these crystals, and that's how impurities are created that can disrupt the structure of a crystal. Sometimes it can just make like a slight discoloration, like you can see in some like cloudy quartzes, or these impurities can be major enough that they create even a different species of mineral. And this distinction can be seen in minerals such as quartz and amethyst, which are the same mineral except for the fact that amethyst has iron impurities in the silicon dioxide structure. Basically everything I've said so far has kind of been in relation to like volcanic activities, but that is definitely not the only way that they can be formed. For example, they can precipitate out of water, and sometimes there are aqueous ions that are floating around in the ocean, and they can either react with other ions in the water and precipitate, in which they form a crystal that is like non-soluble in water, and then it immediately turns solid and floats down to the bottom of the ocean. Or what can happen is the water will evaporate from like a still water pool, and the minerals in that pool of water will kind of condense as the water becomes oversaturated and eventually come out of the liquid. And these minerals are called evaporites and are usually more soluble in water. There are a lot of other conditions in which minerals can form. However, these are the most common, and I can't cover all of them in this short of a time. But the principle between pretty much all of them is still similar. Ions will be present in aqueous or liquid state, and when a change in condition occurs, it causes them to solidify. And once a sufficiently sized crystal formed, the process can speed up as the crystal has more surface area present, where ions in the liquid or aqueous solution can react with the already established crystal. So as these minerals crystallize, they form themselves into lattice structures, which you might have heard me mention earlier, and that pretty much is just like a repeating pattern of the same ions. And these lattices can be made of ionic bonds, metallic bonds, or covalent networks. And the shape of these lattices is often determined by the conditions in which they're formed. What I mean by this is that, for example, graphite versus diamonds, both of them are composed entirely from carbon, but you might know that diamonds are formed deep underground where the pressure and temperature is extremely high, and under these conditions the carbon atoms can squeeze together so tightly that each carbon bonds to 4 other carbons, which requires like an immense amount of pressure. And this kind of creates a tetrahedral structure where there's a central carbon with 4 carbons attached around to it, and every single carbon is its own central atom relative to the carbons around it. And this creates an extremely strong lattice that holds together, and that's kind of the reason for why diamond is the hardest material known to man. Whereas graphite, which can be formed in much less extreme conditions, only has 3 bonds per carbon, and this means that there are a lot of trigonal planar structures which are 2D, well, not actually 2D, but as close as we can get to 2D. So each graphite is only has 3 bonds, and it basically just makes a flat sheet, and these individual sheets are extremely strong, just like diamond. However, the multiple sheets stacked together are only held together by London dispersion forces, which are much weaker. And at first it might seem confusing how graphite is as strong as it is despite being held together by London dispersion forces, but the massive amount of surface area that's made by these long and extremely strong graphite sheets means that it can stay solid. However, they still do flake off much easier than it is to break an individual layer of graphite. So basically what I'm getting at is that these differences in structures where the elemental composition is the same can end up leading to extremely large differences in properties, including like transparency, color, hardness, and luster, all of which are different between graphite and diamonds. A more tangible example of the effects of the bond type is what the crystals look like when it's on a scale visible to the human eye. An example is quartz, or silicon dioxide, as well as ice, which is dihydrogen monoxide. They both have very similar empirical formulas where it's one larger atom and two smaller atoms, and they have very similar crystallization patterns. If you've ever seen like an unpolished quartz crystal, you might see that they always form hexagonal prisms. You may wonder why that is. Basically, it's just because the structure of the quartz on the atomic level resembles that of hexagons too. And if you've ever seen a diagram of an ice-like crystal forming, then you might see that those two form hexagons between the molecules of water. And basically both of them, since they have similar empirical structures, they both form like hexagonal crystals. And you can see that in like snowflakes or when like a glass cools really quickly. And you can see that it forms ice crystals that take hexagonal shapes. The main difference between these two is that quartz is made of a uniform covalent network of silicate tetrahedrons, while ice is made of both covalent bonds and intermolecular H bonds, and that kind of results in an increasing non-uniform behavior of ice crystals when they increase in volume. So earlier on, you may have realized that metals do fit the description of a mineral, and they because they're naturally occurring substances and they form lattices. Metals form metallic bonds with other metals, meaning that the electrons are free to move through the substance, and it also means that the lattice is made entirely of positive ions, and as such it's highly malleable compared to the rigid structures of lattices that are consisting of cations and anions, such as a salt. Malleability is another property that's used to distinguish between different minerals, and malleability is almost exclusively present in purely metallic minerals. A very famous example of this distinguishability is between pyrite, also known as fool's gold, and real gold metal. They look relatively similar at first glance. They're both yellow and they're shiny, but they needed, miners needed to find a way to distinguish between the two. And a way that they found was pretty successful is that they would bite it with their teeth, and if it was real gold, which is made entirely of cations, it would just kind of conform and it would shape to their teeth, whereas pyrite, fool's gold, would be just as hard as any other rock because it's not a metal, it's not purely metallic. It's still got metal in it. So the reason that pyrite exhibits such a similar color is because the primary component of pyrite, which is sulfur, and gold have similar hues. In sulfur, there are no sublevels that have a difference in energy that are equal to a photon of yellow light, which basically means that when white light from the sun or any other source hits it, it will absorb all other colors besides yellow light, and that yellow light will bounce off and be collected by our eyes. And gold is much more massive, and it's got different reasons for why it's yellow, but that's way too complicated for me to understand or explain. But regardless, these minerals are these colors in large part due to the atoms that compose them. And this is noticeable in pretty much any mineral. For example, iron-rich minerals have usually a shade between yellow, orange, or red, or like manganese-rich minerals are usually pink. Another component of this is fluorescence, which is also a result of mineral composition, and it functions pretty similar to the reason that sulfuric elements are usually yellow, or sulfuric minerals are usually yellow. So fluorescence is the emission of a longer wavelength of light as a result of excitation by a shorter wavelength photon. This is most commonly seen by shining a UV light on something and it emits visible light. This is due to a phenomenon called Stokes shift, where there's basically a loss of energy when the electrons are excited from the UV light, and this kind of shifts the wavelength over a little bit, and this energy lost basically increases the wavelength, and it means that the light that's emitted from the mineral is visible to the human eye. So that about wraps up everything I wanted to talk about today, but I wanted to give a little bit of insight into why I decided to choose this topic. So when I was in kindergarten, I had a teacher who would give out little minerals every time that we either read a book out loud to the class or got a good grade on a test. And since then, I've kind of just had this collection of minerals sitting on my desk for a long time, and she taught us a little bit about them. Obviously, we couldn't understand much because we were kindergartners, but I've always just been intrigued by it, and anytime I go into a museum like the Natural History Museum, I'm always kind of gravitated towards the gem exhibit. I just think they look nice, and I've always kind of wanted to understand the science behind it, and I think that this was just a good opportunity to be able to kind of explore that further. So that's enough about me. I hope you enjoyed, and thank you for listening.